Hi, this is our first video on depth-first search. This video is going to cover some preliminary ideas and kind of a first draft of depth-first search that's going to have a problem. In the next video, we'll see the final draft that addresses that problem. So we're covering depth-first search here. We call that DFS. It's the letters of those words. The goal is to traverse a graph starting at a defined start vertex. So the input to depth-first search is a graph and a start vertex. The depth-first terminology comes from this idea of doing a deep dive into the graph far away from start. So there's a start vertex and we kind of run away from that as fast as we can until we hit a dead end, and then we deal with the dead end. In order to avoid getting stuck in an infinite loop, we have to track which vertices we've seen. And we're going to use that word seen, unseen. A seen vertex is one that we've dealt with, an unseen vertex is one that we have not traversed yet, and we have to keep track of that to avoid looping around forever, because a general graph can have a cycle in it. So in depth-first search, when we reach a dead end, so a vertex that has no unseen neighbors, so there's no local area we can traverse into anymore, we back up one step and do another deep dive. An analogy might be some kind of like a web surfing rabbit hole. Those of us who surf the web have probably had this experience before, where you start in one page and you keep clicking and you end up somewhere totally different. So maybe I'm curious about the Labor Day holiday, and I start on that Wikipedia page, and oh, I see something interesting. I click a link, I click a link, I click a link, and suddenly I'm learning about the French Revolution or something completely unrelated. So that's kind of the depth-first search idea. You have a starting point in the graph, but you click away from that as fast as you can until you hit a dead end, and that means you move pretty far pretty fast. Okay, so depth-first search kind of naturally has a recursive structure to it, so we can implement it as a recursive algorithm, and we're going to start there. So first we mark every vertex as not seen, because again we have to keep track of which vertex we've dealt with and which one we haven't. So to begin with, they're all not seen. We record that in a data structure of some kind. Then the depth-first search algorithm on graph G starting at vertex start is first you visit the start, you mark start seen to record that, and then for every out edge from start to V, so this is every edge that starts at start and goes to a neighbor, V. If V has not been seen yet, we do a recursive depth-first search on V. So that's the algorithm. Now, I'm going to run it by hand on an example, but before we do that, we have to clear up one source of potential confusion, which is the order that edges are listed. So we'd like to be able to traverse graphs by hand. I'm going to do that exercise in a moment. We're going to do some exercises like that in our class. And we'd like a deterministic process. Deterministic means that every time we do this process, we'll get the same exact outcome. So if I run depth-first search by hand, I'll get a certain traversal, a certain ordering of the vertices. If you do it, you'll get the same order. That's just so that we can give each other feedback and have exam questions that have definitive answers and things like that. So in order for that to happen, we need to have a defined order that out edges lists the adjacent vertices of I. So out edges was this operation in the graph abstract data type. You give it a vertex index I, and out edges returns a vector of every j such that there's an edge from I to j. This would come up on this step here, the for loop in the depth-first search algorithm for each edge going from start to V. So in order to get that list of vertices going from start to V, we would call out edges on start. Now, the order that out edges returns the vertices impacts the order that the depth-first search will proceed in, but the abstract data type for the graph does not specify what order that has to be. This is the language of that definition right here. It says return a vector of every j where there's an edge from I to j. It doesn't say what order those have to come in. So a graph data structure is free to pick whatever order it wants. We gave it that freedom to keep things efficient, but now that's a bit of a challenge when we're trying to run this by hand. It happens that the adjacency matrix would always return those vertices in increasing order. If we think back to the details of how adjacency matrix worked, the out edges operation involved looping through every vertex in a row. So we go through every column from 0 through n-1. Usually we write those for loops in that order, 0 through n-1. And if that entry in the matrix is true, then we add that vertex to the vector of out edges. So if we have a conventional for loop that starts at 0, works its way up, then adjacency matrix will actually always return those in increasing order. The adjacency list is a more complicated story. Remember that it has a singly linked list for the out edges of a given vertex. And the way that we implemented that was that when you add an edge, we put that new edge entry at the beginning of the list. So that means whatever order you call the add edge operation, the lists will be in the opposite order, the LIFO order, because we're adding to the front, kind of like a stack. So the order of out edges is defined. It's the opposite of the order you added the edges, but that's kind of confusing, and we don't really want to get into that detail. Like if I say let's do depth first search on this graph, I don't want to have to also tell you what order each of these individual edges was added so that you could reconstitute that. So instead, we're going to define a convention that when we do one of these graph traversals by hand, we're going to assume that out edges returns the vertices in increasing order. So if I do out edges of 8, it will return 5 and then 7 in that order every time, increasing order. 5 is lower, 7 is higher. If I do out edges of 6, the out edges are 7 and 9. In truth, the data structure might return 9 and then 7, or it might return 7 and then 9, but for the purposes of doing this exercise by hand, we'll assume that the out edges go 7 and then 9 in that order. Okay, so now let's do a depth first search by hand. I'm going to run this algorithm on this graph. So G is the graph in the top right corner. 3 is the vertex we're starting at. You can start from any vertex. I'm choosing 3. Incidentally, I'm not choosing 0 because often these examples start from 0, and that might give you the impression that you always have to start from 0. But that's not the case. You can start from any vertex. We're starting from vertex number 3. So first off, we mark every vertex as not seen. I'm going to denote that a vertex is seen with a green check mark. So to begin with, none of the vertices have a green check mark. That means they are not seen. First thing that we do is a depth first search on 3, the start vertex. So we do depth first search of 3. We visit 3. So 3 is the first vertex visited. I'm going to make a list of the vertices that we visit in the order that we visit them. So 3 is the beginning of the list. Here's that green check mark. We have seen 3. We don't need to visit 3 a second time. Then for every out edge starting at 3, so there's 2 of them. There's an edge to 1. There's an edge to 4. Our convention from the previous slide is that we'll do 1 first and then 4 later. So now we do a recursive depth first search starting at 1. So mark it seen, add it to the list. And then for every out edge from 1, we're going to recurse into it. There's only one edge out of 1, which leads to vertex 2. So now we do a depth first search at vertex 2, add it to the list, mark it seen with a green check mark. Now we do this loop. This is where this check comes into place, this mark. We do execute this loop for every out edge, but there's only one out edge to 3, and 3 is already seen. So we do not do a depth first search into 3. And that's important because if we did, we would get into an infinite loop. You know, what we just did was we started at 3 and we ended up back at 3 again. That can happen because these graphs can have a cycle. But if we did another recursive depth first search at 3, we would go through the same process. We would go through these 3 vertices end at the same place, loop around forever. And we don't want that to happen. So that's the purpose of this mark in this if statement. So depth first search on 2 finished and returns back to the depth first search on 1. 1 finished, looping through all of the out edges, so now we're back to 3. So now we're back in the original depth first search on 3. The first iteration of this loop did the recursive search into 1, and then the second iteration is going to do a recursive search into 4. So now we do a depth first search on 4, add 4 to the list, mark it off as seen, and loop through every out edge of 4. There's only one of them to 0, so we visit 0, mark it seen. And visually, as a human being, I can tell that we're done. The algorithm hasn't quite figured that out yet. There's a few more steps for that to happen. So 0 would loop through all of its out edges, and there's one out edge to 1, but it's already seen, so that loop does not recurse. We return out of the depth first search of 0 back to the depth first search of 4. That loop finished. There was only one vertex to recurse on, and that is finished. So that recursive call terminates and we go back to the original depth first search on vertex 3, and it's done. It had 2 out edges to loop through, and it finished both of them. Okay, so that works. That's one version of the depth first search algorithm that we just went through. However, there's a flaw in it if we try to implement this in the C++ programming language. This algorithm can overflow the stack if you have a very large graph. The reason is because every time this recursive algorithm starts, it puts something called a control frame on the control stack, and if you have a very large graph, we won't start popping off the stack until we get pretty far into it, and if you have enough vertices, this can overflow the stack. Basically, if the number of vertices is greater than the size of the stack, that could happen. I'll note that this is not a flaw in the algorithm itself, it's a weakness of the C++ programming language. There are other programming languages that have something called the tail recursion optimization. For example, the Lisp programming languages have tail recursion, and in those programming languages, in a situation like this where an algorithm calls itself as the last thing it does, they don't overflow the stack in that situation. They're more sophisticated in that way. So if we could implement this version of depth first search in one of those algorithms or one of those programming languages that have tail recursion, but C++ is not one of them. So we will have to do this in a different way that doesn't overflow the stack. And to do that, we'll convert this recursion into a loop. We won't use a recursion. Instead, we'll have a loop. We still need to keep track of which vertices still need to be seen. That's being done automatically with the control stack and the recursion. You know, when one of these for loops ends and we return out of a depth first search call, we return back to the parent call, and that keeps track of what work still needs to be done. If we switch to a loop, our algorithm has to keep track of that itself. So we're going to have to add a data structure to keep track of that, and it's going to be a stack to mimic the stack behavior of the control stack in this recursion.